Okay, it's going to ask me for consent, I think, or maybe not. Okay. All right, so welcome everybody to my, third or fourth series of talks here. If you don't know, I'm slowly pushing my way towards learning Fermat's last theorem to a relatively deep degree. I intend on this taking something like 6 or 7 years, and I'm a little over a year in. In my most recent studies, I've actually really started looking at elliptic curves and modular forms a little more carefully, which are the key ingredients to the proof of the modularity conjecture, which implies Fermat's last theorem. And in particular, I started looking at this problem called the congruent number problem because I hosted a reading group on my Discord, Brian Grove and my Discord, reading Koblitz's book called Introduction to Elliptic Curves and Modular Forms. And he basically goes more or less through the entire proof of the congruent number problem. He does leave out a few things, so I did have to consult a few extra sources, but that is what this talk stems from. This is kind of like a Fermat's last theorem light. This is a highly non-trivial theorem, but it's certainly much easier than Fermat's last theorem will be. And so let me get started here by just giving a quick introduction. So we're basically going to go through the proof of Tunnel's congruent number theorem. I'm a big believer in stating the theorem you're going to prove before you give a talk. But this theorem is so surprising and shocking to me that I'm actually not going to state it. You're free to look it up on your own time. I would recommend you don't, though, because when we actually get to it, I think you will be very shocked at what the theorem actually says. This is a good theorem to study if you want to study elliptic curves and modular forms, because you need all the basic tools from elliptic curve theory and all the basic tools from modular form theory to actually get this result. And so this is an excellent result to study those topics. And as many of you know, elliptic curves and modular forms, those are like really key objects in modern number theory. And as I said earlier, they're crucial in the proof of the modularity conjecture and thus Fermat's last theorem. For those of you who don't know what the modularity conjecture says, it says every elliptic curve over the rationals is modular. And we will actually see exactly what that means. We will see one incarnation of what that means. There are many different ways, avatars of that statement, but we will see one completely rigorous instance of what that means later. So let's start with, let's break it down into the two different objects, elliptic curves and modular forms. Let's first talk about why elliptic curves are important in the first place, like why would you bother? There are different perspectives here. So the first perspective would be the naive kind of classical number theoretic perspective. And that would be, okay, well, we want to solve equations. We want to solve Diophantine equations or equations over the rationals. That's just what we want to do as humans. We want to find the roots of equations. Okay, so what would you do? Well, you'd probably start with equations in one variable and try to solve those, right? And you'd probably start with linear and then quadratic and so on and so forth. The thing is, one variable equations are very well understood thanks to Galois theory, for example, the insolvability of the quintic and things like that. And then also just general techniques about solving equations. We pretty much as a species have a good handle on what it means to solve a variable an equation of one variable. So then what do you do after you understand how to solve equations of one variable? Well, you go on to equations of two variables. And I'm not going to get into any of this, but it turns out that quadratics in two variables are basically completely understood. So what do you do after you solve quadratics in two variables? You move on to cubics. And of course, you expect some jump in difficulty, but you're not bargaining for what you actually get. As soon as you move to cubics in two variables, things get much more complicated. And elliptic curves are basically examples of cubics in two variables. For example, you can show that every cubic over the rationals in two variables can be written in this form here. This is a Weierstrass normal form. We'll talk more about this later. So y squared equals x cubed plus ax plus b after some suitable number of rational change of coordinates. So when you're studying cubics and two variables, it really suffices to work with equations like this. And once you projectivize these, which we'll talk about later, essentially all that means is you're adding a point at infinity. And I'll make that precise in maybe even today, I'm not sure. So once you projectivize them, once you give them a point at infinity, and then once you require that they're smooth, which it turns out is the same thing as this cubic over here having 3 distinct roots, then what you've got is an actual elliptic curve. So an elliptic curve classically is an equation of this form that is smooth and projectivized. So it has a point at infinity. So I don't really like this motivation though. I don't really like the whole, okay, well, we understand 1 variable equations, so let's move on to 2 variable equations. Oh, and we understand quadratics, so let's move on to cubics. That somehow makes it seem like, okay, if we could just get done with cubics, then we could go on to quartics. And there's nothing inherently special about elliptic curves. And that is not the case. Elliptic curves are very special, so it's useful to have other perspectives other than this one. So what you have to realize is that elliptic curves have very rich algebraic and analytic properties that even curves of higher degree don't have, and that curves of lower degree don't have. So even if you were able to somehow solve every elliptic curve, you might not get everything you need out of elliptic curves before moving into quartic territory. So it's useful to stop and ask, is there anything special about elliptic curves? There is. So first of all, there's the complex analysis perspective on elliptic curves. If I look at elliptic curves over the complex numbers, so elliptic curves that have complex coefficients, it turns out that every complex elliptic curve is biholomorphic and group isomorphic to a complex torus. So if you're asking me why are elliptic curves important, you're essentially asking me up to biholomorphism, why the torus as a shape is important. And I think we can all agree that the torus is very important. It's the simplest example of, a nice one-dimensional complex manifold with a hole in it. And then in turn, so you can also check this is trivial, but you can check that tori are really the same thing as lattices in the complex plane, or even in the upper half plane. So if you agree tori and lattices are important objects, which, if you're a discrete mathematician, you agree lattices are important. If you're a complex geometer, you agree tori are important. If you're any kind of geometer, you agree tori are important. Then you should really already be in agreement with me that maybe elliptic curves are important as well. So that's the number theoretic and the complex analytic perspective. There are more perspectives though. For example, where did elliptic curves even come from? Why are they even called elliptic curves? If you take the Calc 2 formula for the arc length of a curve and you try to apply that formula to an ellipse, you end up discovering that you're in some trouble and you can't get an exact answer. And if you do suitable if you make suitable substitutions in the integral, what you end up with in the denominator is an equation that looks like the square root of x cubed plus ax plus b. So if you call that y and square both sides, what do you get? You get this. You get an elliptic curve. So that's sort of the namesake for why these are called that. And I think that even by itself is a useful perspective to have, even ignoring the previous 2 perspectives. But then, so I'm going to try to keep this talk basically 100% algebraic geometry free, but I'm going to give you the algebraic geometry perspective on elliptic curves because it's it's probably the most useful and most powerful point of view. If you study elliptic curves as schemes, then what you realize is there really is something special going on here. So for example, the classical definition of elliptic curves is equations that look like this that are projective and smooth. However, you can show this is equivalent to the following definition from algebraic geometry. Elliptic curves are exactly the genus 1 regular, just think smooth if you want, genus 1 smooth curves with a distinguished point, which you can think of as the point at infinity. In other words, they're sort of like the dumbest curves the dumbest smooth curves possible, which is already good to know. Well, the dumbest ones would be genus 0, but genus 0 curves are not interesting. So, and then it turns out that if you study all the sheaves of functions on these curves, you end up with wild properties that curves of any other genus do not enjoy. And so you really get to see, no, it's not just that it's the next natural step for mankind to study cubics and two variables. It's that there really is something special going on here. There are many rich sheaf theoretic properties on these things. Here's another thing. You can also show using algebraic geometry that elliptic curves are these very special objects called abelian varieties. And you can even also additionally on top of that show that they're in some sense the simplest type of abelian variety. So I'm not going to go into what that means, but once you study abelian varieties, you'll agree that they're important. And so then when you want to study an entire class of objects, you should want to start with the simplest ones, right? And if there's a notion in which, with which elliptic curves are the simplest abelian varieties, then those are exactly what you ought to be studying first. So there's like 4 or 5 different perspectives on why you should care about elliptic curves. And there are more, by the way. I mean, there are other reasons. I do not claim that this is some kind of exhaustive list. So that's an introduction to elliptic curves. What about modular forms? This is a little bit harder to motivate, but I'll try my best. So why do we care about modular forms? A simple but unsatisfying answer, although it's actually, in a very real sense, it's the most correct answer, but they are large classes of holomorphic functions on the upper half plane with deep and rich symmetries. The only reason, this is a great answer, but the only problem with it is like, okay, well, what led us to study these things in the first place? How did we discover these functions with deep and rich symmetries? Well, the history is a little dicey. You talk to any 2 people, you get 2 different answers. I'll give you some things that I found out. First of all, and we're not going to talk about this in this talk, but it turns out you can endow every modular form with something called a Galois representation. But also conversely, if I give you a Galois representation, whatever that is, there is a way where you can sort of see that as arising from a modular form. And so if we all agree Galois theory is important, which I think we all do, then this is some motivation that modular forms should be important. If we can attach basic objects from Galois theory to them and conversely, then probably there's something there to study. But there are other ways to arrive at the study of modular forms. For example, you can look at the complex exponential function in conjunction with certain lattices in the upper half plane. And modular forms pop out very naturally from this study. So if we agree the exponential function, the complex exponential function is important, and we agree lattices are important, then we probably agree that their interaction is important. And so as a result, we should agree modular forms are important. And I also want to make a point here. Lattices were one of the motivations I gave for elliptic curves being important. And it's actually no coincidence that lattices also show up as a motivation for why elliptic curves are important, because there are very deep connections between elliptic curves and modular forms. And this leads me to my last motivational point, which is the reasons to study modular forms are sort of parallel with the reasons to study elliptic curves because they're so tightly interconnected. Okay, so for example, I told you that elliptic curves are the easiest examples of things called abelian varieties. Modular forms are also the easiest examples of a certain class of functions called automorphic forms. Okay, and so I know this answer is going to be unsatisfying also, but in the modern view of things, it's probably the most correct answer. And it's, why do we study modular forms? It's because they have deep connections to elliptic curves, and we all agree elliptic curves are important. So I know maybe if you combine all of those answers, you'll be satisfied. But so for example, the modularity theorem of Wiles, every elliptic curve is modular. That's a statement that's a very deep connection between elliptic curves over the rationals and modular forms. And there are many others, and we will see some of those in this talk. So don't worry if you don't know all the terms I said. It's not important. I just wanted to give you some motivation here. And so that being said, I'm done with the introduction. We can actually get into this now. Hopefully you believe we should actually be studying this. So, oh, thanks, Sunil. I didn't see that you popped in. History of EC, right, yeah, okay. Okay, so we're gonna start by looking at what it means for a number to be congruent. What is a congruent number? We say a natural number is congruent if there's a right triangle with rational side lengths whose area is n. Okay, so basically a number is congruent if it's the area of a right triangle with rational sides. You may have seen this if you studied kind of basic number theory. You may have seen this in the context of Pythagorean triples, which are integers x, y, and z such that x squared plus y squared equals z squared. So what are Pythagorean triples in the context of congruent numbers? Well, instead of requiring that the side lengths to our right triangle be rational, we're basically, when we look at Pythagorean triples, we're asking that they be integers. Okay. And how do we know we're looking at a right triangle here? Well, this is just the Pythagorean theorem, right? So z is like the hypotenuse, and x and y are like the side length, the leg lengths. So if you've never seen this before, I'll just give you a crash course in it. How do you generate all the Pythagorean triples? What you do is you draw the unit circle. Okay, maybe I can even draw this somewhere. I don't know. Let's see. Okay, so you have the unit circle, great. And what you do is you look at the point -1, 0. Wait, I got to stop this. Okay. Right. And you draw a line with rational slope b over a through the point -1, 0. And what will happen is you'll hit some other point on the circle. Okay. Maybe up here. And you can and if I give that point coordinates u comma v, you can easily figure out in terms of the slope b over a what the coordinates are. And I gave you the formula right here. So so you can check that the x coordinate of the second point has to be a squared minus b squared over a squared plus b squared. And that the y coordinate v has to be 2ab over a squared plus b squared. Okay, so once you've done that, how do you get a Pythagorean triple out of this? If you let x be a squared minus b squared, y be 2ab, and z be a squared plus b squared, you can show that those form the sides of the right triangle. In other words, they satisfy this relationship up here. So that's how we get some Pythagorean triples. How do we get all of them? Well, I'll leave that as an exercise for you. Check that if you take this right here, and you allow a and b to range throughout the entire set of natural numbers, with the only restriction being that a is bigger than b, then actually you don't just generate some Pythagorean triples, you generate all of them. Okay. So that's the Pythagorean triple problem. The congruent number problem is slightly, well, it seems slightly more general, but it's actually much harder. We're interested in right triangles with rational side lengths, not necessarily integer side lengths. And so our question is going to be, if I give you a natural number, can you tell me when it's congruent? When is it the area of a right triangle with rational sides? Now, if I asked you to do that right now, you'd say, there's no way this is checkable. I would have to check. I mean, sure, there might be restrictions on the rational numbers that I'm checking, but certainly I have to check infinitely many pairs, infinitely many triples of rationals, x, y, z. I've got to make sure they constitute a right triangle. And then on top of that, I've got to make sure that their area is n. Certainly, this cannot possibly be a checkable process. And if it is, there's no way it terminates in any reasonable amount of time. Well, we're going to see that is not the case, or almost not the case, okay, as we go through this. So this is the main question here. When is a natural number congruent? It's a hard question. It's a very difficult to get an actual reasonable answer, but we're going to slowly whittle it down and get it to the point where we actually get a very beautiful answer here. Okay. So the congruent number problem seeks to find a checkable terminating process to answer this question. I should be able to plug my number n into a computer program, and in a reasonable amount of time, preferably more or less instantly, it should be able to spit out the answer yes or no to whether or not this natural number is congruent. Okay. And I think at this stage, we're all thinking this is unreasonable, but we'll see it's not. In the process of developing this theorem, we're going to have to dive very deeply into two rabbit holes, or maybe three rabbit holes if you like, the rabbit holes of elliptic curves and their L functions, and then the rabbit hole of modular forms. Now, you might have heard me say a second ago that this problem is kind of mostly solved. The reason is there is one hurdle. The theorem is of the form, a natural number is congruent if and only if something. The problem is one direction of that if and only if relies on a weak version of a millennium problem. Okay, so that millennium problem is the BSD conjecture. It's a very weak version of it, but nonetheless, even this weak version is not solved, although I will share with you the progress that has been made once we get there. And you might say, well, okay, so which direction of the if and only if is it? Is it the direction where we start with n is congruent and we end up with a nice condition? Or is it the direction where we start with this nice condition and end up with n is congruent? Unfortunately, it's the latter, which is the one we really want to be true. But I think you'll agree with me that BSD conjecture is most likely true. In fact, there are some results as of 2015 on its truth. And so I think that even though the term millennium problem shows up here, you will agree with me that this is not actually that formidable, that large of a hurdle, in the sense that since it's so likely to be true, we can be pretty sure that the congruent number theorem is true. That will be our only hurdle. Okay, and it only really breaks down one of the directions of the congruent number theorem, not the other. Okay. So let me go on and start here. Let me give you a more general definition of a congruent number. Let me tell you what it means for a rational number to be congruent. I told you what it means for a natural number to be congruent. What about a rational number? It's the same definition. So a rational number is a congruent number if it's the area of a right triangle with rational sides. Introducing and generalizing this definition seems to broaden our problem, but in fact, it will narrow it. Here's why. Let's say I have a congruent rational number, and let's say the sides of the right triangle are x, y, z. Okay. Okay, what you can do is you can do this for any rational number. You can locate another rational number s, such that when you do s squared times r, you get a square-free integer. Okay, you're basically canceling the square part in the denominator, and you're basically canceling the denominator and removing the square part at the same time by multiplying by a suitable rational number. And so you started with a rational congruent number, right? And you ended up with a square-free integer congruent number. How do we know it's congruent? Because you can check this, it's trivial. If x, y, and z are the sides of the original triangle, sx, sy, and sc form the sides of a similar right triangle whose area is our new congruent number, s squared r. So hence, by broadening our definition of congruent number, we actually have narrowed it down. We've seen it suffices to not only study integer congruent numbers, but actually square-free integer congruent numbers. You mean that the criterion therein is conditional? Right. Yes, Sunil's right. I said that a little bit wrong. Tunnel's theorem is completely correct. It's just that we cannot use it as an actual algorithm for testing congruence unless a weak version of BSD is true. So here's an exercise if you want to try one. A Huronian triangle is a triangle. It's not necessarily a right triangle, just a triangle with integer side lengths. Show that the area of a Huronian triangle has to be divisible by 6. So that's an interesting little problem. Okay, So now we've seen that when we're talking about congruent numbers, it suffices to work with square-free integers. So our next goal is when is a square-free integer congruent? And that leads me to right here. So here's the first proposition. The first proposition is the following. Suppose I have three rational numbers, x, y, and z, with x less than y less than z, and then I have a square-free natural number n. Then the right triangle with leg lengths x and y and hypotenuse z and area n, triangles of that form are in bijection with numbers x such that x and x plus or minus n are squares of rationals. And I'm not going to prove this, but I mean, here's the proof. Here's the correspondence. Wait a minute. Right. Yeah, here's the correspondence. Okay, so if you want to look more into that, you're free to. And there's a nice succinct way of summing this proposition up into the congruent number language, and it's this: n is congruent if and only if there exists a number x such that x and x plus or minus n are squares of rationals. And that's just an immediate corollary of this proposition. And this proposition is not that hard to prove. Not only is it not that hard to prove, it was well known in ancient times, actually. So the congruent number problem has been studied for centuries, and this has been known for centuries. I forget who it dates back to. I know the Greeks knew about this, but I don't know if it even went further back than that. Okay, so here's one condition. If you can find some number, x, such that x and x plus or minus n are squares of rationals, you've got yourself a congruent number. It's just that this isn't really more checkable, right, than the definition of congruent number itself. You're still checking through infinitely many rational numbers. But I guess the nice thing about this compared to the initial definition is that you're only really checking x, right? In the initial definition of congruent number, you're checking triples of numbers x, y, and z. So in that sense, I think this is pretty nice. It's just not nearly good enough. Okay. So like I say here, this result's not that powerful, but what it leads to pretty quickly is what we're going to end up being concerned with. So if you study the proof of this proposition, what you end up discovering is that if x, y, and z are the sides of a right triangle with area n, then this equation must be satisfied here. Okay, so x plus or minus y over 2 squared has to be z over 2 squared plus or minus n. It's a very elementary check. There's nothing deep there. But what you can do is you can take this and you can manipulate it. And here's what you'll do. Assume n is congruent now. Let x, y, and z be the sides of this triangle whose area is n, right? This right here is two equations. So what you do is you write the two equations separately and you multiply them together. So the equation with the plus here and the equation with the minus, multiply those together. And what you find is the equation u to the fourth minus n squared equals v squared has a rational solution in the event n is congruent, given by u equals z over 2, and v is x squared minus y squared over 4. Again, this is just elementary algebraic manipulation. Okay, so this equation right here has a rational solution, u comma v. Now, take this equation here and multiply both sides by u squared. And what you get is this expression right here. U to the 6th minus n squared u squared equals uv all squared. Now, n is congruent, right? So from proposition 1, there's this number x, such that x and x plus or minus n are all squares of rationals. So what we're going to do is we're going to set that x equal to u squared, which we know from up here is z over 2 squared. And then we're going to introduce a new variable y, and we're going to call y uv, this uv that pops up right here. And you can check using this expression here for u and v that y is just x squared minus y squared all times z over 8. And what you find is, you know that x is rational because it's z over 2 squared, and z over 2 is rational. and clearly y is rational. So what you have found is two rational numbers, x and y, satisfying the following equation. If we make the substitutions I said, this equation up here turns into the equation y squared equals x cubed minus n squared x. And you might recognize and suspect this is an elliptic curve. Okay, so we will see this is actually an elliptic curve, provided some very stupid assumptions are satisfied. Okay, so what does this tell us? Let's summarize. If I give you three rational numbers and they form the sides of a right triangle with area n, then you can locate two rational numbers, little x and little y, satisfying this elliptic curve here. Y squared equals x cubed minus n squared x. Okay, so that's interesting. Of course, we wonder, is the converse true? If I have a rational solution to this curve, x comma y, does this admit three rational numbers that are the sides of a right triangle with area n? And the answer is no. And so you might think that's a big hurdle to overcome. It's actually not at all. Because you can actually figure out how to fix this in the following way. You can show, again, it's not very hard at all, a necessary condition for such a solution, okay, to come from a right triangle, so to kind of reverse this correspondence that we came up with up here, is that x is the square of a rational and that x has an even denominator. And it turns out the converse is true. Okay, so that leads us to the following proposition. Two rational numbers, little x and little y, satisfy this elliptic curve here. I'm sorry, let x and y satisfy this elliptic curve. And suppose x is the square of a rational and has an even denominator. Then there exists a right triangle with rational sides and area n corresponding to x under the correspondence from that first proposition up here. So in other words, points on this elliptic curve that satisfy this condition on x are in one-to-one correspondence with right triangles with area n and rational side length. Okay. So I wrote that here. We've discovered a correspondence between congruent numbers and certain points on this elliptic curve here. And by certain points, I really just mean there's no real restriction on y here, right? The restriction is on x. X has to be the square of a rational and have an even denominator. Okay. And so, okay, so we've got this nice curve here. Before we can actually go any further, we have to understand a little bit about elliptic curves, or else the results that we're going to use to push the congruent number problem even further are going to make absolutely no sense. So let's look at elliptic curves. First, let me give you the full definition of a elliptic curve, classically speaking. So we're going to take K to be a field which has a characteristic not 2, okay? And that really just has to do with smoothness conditions on the curve. Remember earlier I said we want our curves to be smooth. It also actually has to do with normalization, but I'm not going to get into that. A function in the polynomial ring over K in one variable that's a cubic, it doesn't necessarily have roots in K, but maybe it has roots in some field extension of K. Okay. If these roots are distinct, which turns out to be the same thing as smoothness, then we're going to call expressions of the form y squared equals f of x an elliptic curve over K. Okay. And you can talk about the solutions to this curve, but more precisely, you can talk about where do the solutions live? In which field do they live? They don't all have to live in K, right? Unless K is algebraically closed, they might live in some extension of K. The solution, this should be bolded, but the solutions in a field extension K prime over K are going to be called K prime points. Okay. So if your solution happens to live in K itself, we would call those K points. So if K is like the rationals, we would say the solutions that live in the rationals are Q points or rational points. Okay. You can readily check according to our definition here. It's, well, I mean, there's nothing to check, right? This is an elliptic curve because it has 3 distinct roots over the rationals. Namely because what can you do here? You can just factor an x out, right? And then you have a difference of squares here that has two different roots, plus or minus n. And this is an elliptic curve over Q. In fact, it's an elliptic curve over any field K of characteristic P where P is a prime number, as long as P does not divide 2n. And again, that comes down to smoothness reasons, okay? In fact, you should check this. You should check that there's a, check this. Check there's a problem when P divides 2n. Check this is a problem. Okay. If you want to know why these are called elliptic, ask me later. You know what? That sentence shouldn't even be in here because I already got into that. I wrote the introduction to this talk after I wrote the talk. So this actually just shouldn't be in here. Okay. So let's take a curve now, a function of two variables. We'll call the curve C, and we'll say it's given by capital F of x, y equals 0. This, I'm not saying the curve is elliptic though, just some curve, okay? Now let's say we have a K prime point on the curve. So some point x naught comma y naught, x naught and y naught live in K prime, some extension of K, and they solve the curve. We say C is a smooth curve at this point if the partial derivatives of capital F are not both 0 at this point. And you can check this. You can check that if K prime is, for example, the real numbers, that this is just the usual notion of the existence of a unique tangent line at this point. Okay, so this is the correct definition of smoothness. Okay, although in fact this is more of the definition of regular, but over suitably nice fields, they're the same notion. So okay, so let's look here. So what situation are we in? We are in the case, what does our curve look like? If we were to write it in this form, we would write it as y squared minus some little f of x as our capital F, okay? In our case, little f is this cubic here, but in general, it's just something, okay? What are the partial derivatives of this? The partial derivatives are 2y and negative f prime of x. Oh, you know what? So I'm spoiling this problem that I gave you, but I'm going to spoil it anyway. Since the characteristic of our field is not 2, when will these both vanish? These will both vanish if and only if y is 0 and x is a multiple root of f, right? Because roots of f prime, roots of f and f, roots of f that also are roots of f prime are double roots of f. So this is why we insisted our elliptic curves had distinct roots in the original definition. It's because by this little analysis here, having distinct roots is equivalent to not having multiple, having distinct roots is equivalent to smoothness. Because when you have a multiple root, both of your partials vanish and vice versa, okay? So we wanted smoothness everywhere. We don't want to be working with degenerate, like stupid curves with singularities. Okay, we want smoothness. But anybody who studied projective geometry realizes that there's no reason to actually study this curve right here in the form that it's written. You may as well projectivize it. And what does that mean? What you want to think of when I say projectivize is we're adding a point at infinity or a distinguished point. Practically, what you want to think about, though, is you want to make it so that each term in this curve has the same total degree. So like, this y squared term has total degree 2. This x cubed term has total degree 3. This x term has total degree 1. We would just like all the terms to have total degree 3 because then this polynomial is homogeneous and we can use the nice properties of homogeneous polynomials that we know. How do you do this? You effectively just multiply each term by z to an appropriate power to make each term have degree 3. So, you know, if you want y squared to have degree 3, you'll multiply by 1 copy of z. If you want x to have total degree 3, you got to multiply by z squared. X cubed, we don't have to multiply by anything because it's already degree 3. You can check that since this is a homogeneous polynomial, scaling these variables by non-zero constants in our field doesn't affect the 0 locus of this curve. So you can actually replace y, z, and x by multiple non-zero multiples of themselves, and the 0 locus is unaffected. That's one of the nice properties of homogeneous polynomials. So what does that mean? That means discussing whether or not this curve is 0 at a triple xyz can be discussed up to non-zero scalar multiplication, which is very nice. That's something you can't do in the affine case up here, okay? And you don't lose any solutions by projectivizing, but you do gain one. You gain the point at infinity, which is the triple 0, 1, 0. You will see that that satisfies this, okay? And that point is called the point at infinity, okay? And I just want you to note that 0, 0, 0 doesn't live in the projective plane. If we're viewing this as projective, that means it lives in the projective plane. 0, 0, 0 doesn't make sense in the projective plane. At least one of the coordinates have to be non-zero, because points in the projective plane, what are they? They're lines in affine space, okay? And there's no line corresponding to the origin, okay? There's no line through the origin corresponding to the origin. That just doesn't make sense. Okay, so basically we're projectivizing our curve, which adds a solution at infinity, which is this point here. And but I'm not going to write this from now on. From now on, I will simply write y squared equals x cubed minus n squared x, but we will all agree that I mean actually the projective version of it, okay? One way to think about the point at infinity is if you draw like a generic elliptic curve, you see there's always the symmetry about the y-axis, and then you also see the slopes always blow up to infinity. So what people tend to do is they tend to imagine there's some kind of point lying out there that this curve goes through. Some people also associate the point at infinity to a vertical line tangent to the curve at the appropriate spot, but that's neither here nor there. We don't need to get into that discussion. Okay. So just be aware, unlike regular points, x comma y, 2 points on the projective version of this curve are the same if and only if you can get the coordinates of one by multiplying the other by a non-zero scalar. So for example, 1, 2, 3 would be the same thing as, I don't know, 2, 4, 6 in the projective plane, because you can get the coordinates of the second point just by scaling these coordinates by 2. Okay. And as a concluding remark, you may worry that because we projectivized our curve and added in this third variable z, that the notion of smoothness somehow changes. But in fact, it really doesn't. You can check, and I'll leave it as an exercise. It's not hard at all. You can check that the notion of smoothness of our elliptic curve at a point xyz in the projective plane, you can say xyz is a smooth point on this curve if and only if it does not vanish all 3 partial derivatives at once, which is exactly what we expected, right? This means that we didn't really deviate from the affine criteria for smoothness, which was just that our 2 partials didn't both vanish. Okay. Let's see. Let me go just a couple more minutes here, and then I'll just stop and take questions. So we want to study elliptic curves because we have found ourselves in a situation where determining whether or not n is congruent is the same thing as finding a special type of solution on this elliptic curve, y squared equals x cubed minus n squared x. Okay. To really study elliptic curves, you need to first study elliptic functions. Okay. So I wrote here, as is common in modern number theory, to solve really deep problems, you need to draw from virtually every field of math at once. And so up till now, we've basically been drawing on the theory of elliptic curves in calculus. We're now going to need to draw a little bit on complex analysis to continue. So the first thing we'll do is we'll let L be a lattice in C. What does that mean? That just means the following. So take 2 linearly independent vectors in C over R. So we'll take W1 and W2 in C, linearly independent over R. That just means when you divide one by the other, you don't get a scalar, a real number. Then what you're looking at when you make a lattice is you're looking at the following. You're looking at the set of all nw1 plus mw2, where n and m are integers. Okay. So pictorially, what does this look like? Well, I don't know. Here's my first vector, w1. Here's my second vector, w2 maybe. So what will my lattice look like? Well, it'll basically be formed like this. I'll form this parallelogram, and then all the four corners of this parallelogram will live in my lattice. Why? Well, because this is W1, this is W2, this is 0 W1 plus 0 W2, and this is W1 plus W2. And then what's the rest of the lattice? Just tile the complex plane with these parallelograms. Okay, so I'll do that in like black maybe. So keep doing this forever. Okay, so we got a lattice, and you can see why it's called a lattice, because it makes a lattice shape, right? In fact, you can make lattices in CN the same way. You'll just have more components here, okay? But we won't need to be in CN, so much to the chagrin of some mez, I guess. But okay, so we go here. Okay, there's our lattice. Now, what did we do to make this lattice? We really took the same stupid parallelogram and just copied and pasted it a bunch of times. So what's actually important here? What's actually important is this parallelogram, because you can get the rest of the lattice, or you can get just this parallelogram by just taking the entire lattice, okay, and modding out by this parallelogram. So that leads to the notion of the fundamental parallelogram for a lattice. So the fundamental parallelogram for a lattice L, let's say generated by W1 and W2, is capital pi. And what is it? It's not, you don't want these linear combinations of W1 and W2. What you want is all the linear combinations of W1 and W2 with coefficients living between 0 and 1. And you can see that's going to fill in this right here. So this guy right here is my pi. Okay. Then I can produce the rest of the lattice just by knowing what this parallelogram is. And conversely, I can collapse the lattice to this parallelogram with an equivalence relation. Okay. So what is an elliptic function? Well, that doesn't make sense. I can't say this function is elliptic. I have to say it's elliptic relative to a lattice. Okay. So first of all, to be elliptic, you have to be a meromorphic function on C. Okay, so you're holomorphic except for maybe, you know, some discrete number of poles, and so a function f on C is elliptic relative to my lattice if f is periodic, okay, with period L where L lives in the lattice. Okay, what does that actually mean? That's obtuse language. It's great for calculations, but what does it actually mean? It means the values the function takes on opposite sides of the boundary of the fundamental parallelogram are the same. When we translate by a full lattice point, we should get the same value. So like right here, this point right here, if f is going to be elliptic, f at this point had better be the same as f at this point, because they're opposite each other on the parallelogram. They're directly across from each other. So what you should, another way of thinking about elliptic functions, and maybe I'll leave you with it. I'll get through this exercise here and then I'll take questions. Another way of thinking about them is you should think of elliptic functions as just functions on a torus. And do you see why this is? Yes, you do, because I can take a parallelogram and make a torus out of it just by identifying pairs of opposite sides like this. What's the natural motivation for identifying pairs of opposite sides? My elliptic functions take the same value at points that are identified oppositely. So that's why you can think of elliptic functions as functions on a torus, because this periodicity condition basically means, why don't you just go ahead and glue these points where the function takes the same value anyway? Why don't you just go ahead and glue those together? Okay. And starting next time, we'll use this notation. capital epsilon sub L will be the set of elliptic functions for a lattice. If you'd like, in the meantime, here's a good exercise. I'll end with this. Why don't you check this is actually a subfield of all meromorphic functions, and then check that it's also closed under differentiation. So we will need both of those facts, and neither one of them are very hard to check. So, okay, we'll get into some crazy complex analysis stuff next time. So that'll be it for today. I plan on this time. I mean, look, I got through not even 5 pages, and there's 36. So this talk will probably take several weeks to conclude. But thank you for attending today, week 1. And I'll take any questions or comments if anybody has anything. You can type them in chat. You can feel free to use your microphone. You can do whatever is most comfortable for you. Let's see, do we get any chat comments? Oh, Sunil, I read your comment. Okay. Jim, thanks. I'll hope to see you guys next week. Thanks, Sanmez. Does anybody have any questions I could answer? Thanks, Sunil. Yeah, I was a little worried about the motivational part of this because, like, Koblitz, for example, doesn't really motivate the study of elliptic curves or modular forms for their own sake. So I had to do my own research. Unless you think the congruent number problem is motivation, which it is. Okay, we still got a couple people in chat. Does anybody, or in the call, does anybody have any questions for me? I'll take that to mean I was so illustriously clear that it was just so impeccably done, which I know is not the case, but.
Well, maybe it was the case, and well, at least let's thank the speaker by applauding.
Yeah, just applaud into your mic. No, you don't have to do that. Yeah, thanks everybody. So I think same time next week, we'll just keep going as long as this takes. And I don't think it will always be 5 pages per time, but I think it should be no more than 6. So it just depends on how slow stuff is. Yeah, Kelsey, that's okay. Just listen in, even if you don't follow. You and I have had this conversation. So I have some of my math majors in here, so.
That's fantastic.
Yeah.
Just to comment, I think the motivation was good, and you're right that Koblitz doesn't give you much, but as with many things, a lot of different paths converged at just the right time and just the right place, and took many years to get to something that was this coherent theory of elliptic curves.
Yeah, so
there's no motivation that's the right one,
Right, I find elliptic curves to be highly motivated somehow, but you're right. Like when I read up on the history of this, it kind of seemed like modular forms kind of just accidentally became motivated. You're right, because a bunch of stuff kind of just was happening at the same time. And it was almost like everybody was like, oh, all of this stuff is happening at the same time. Okay, well, they seem very related. And since they're happening at the same time, we're motivated to study kind of across between fields. And then out popped the story of modular forms. I mean, it's if you go on Stack Exchange and read the threads about like the intuition or motivation behind modular forms, you get all kinds of crazy, you get a different answer from everybody, that's for sure. I saw one answer that was like, modular forms are a generalization of the exponential function with no explanation. And I was like, oh, okay. Well, assuming that's true, that's pretty good motivation, but.
Yes, and elliptic curves are generalizations of lines.
Right, exactly. Yeah, it's like, yeah, everything's a generalization of that. Sounds like a snarky answer you would give after you've studied modular forms for 4 years and got a PhD in it. You can just go around telling people, oh, they're just exponential functions, just generalized exponential functions.
It is an unfortunately true statement, however, in the same way that the J function in some ways is a very natural generalization of an exponential function, but
right.
you don't just Yeah, you don't just see it by looking at the J function. It's not there,
Right,
but,
right.
yeah.
In fact, I actually, maybe you can tell me, I don't actually know what's the easiest way for that statement to be accurate, that a modular form is a generalization of the exponential function. What is, I
Yeah.
mean,
I don't know either. And
Yeah. There was no explanation in the thread, so.
So maybe one can take,
I mean, you have periodicity, right? So there's that, but.
right, and maybe one is thinking about the fact that the exponential goes along with the multiplicative group, and then you're trying to draw this parallel between the elliptic curves and the multiplicative group, and sort of what is the nice function to go along with the elliptic curve. But I feel like that's a little roundabout and in hindsight rather than motivation.
Right, right. Yeah, it's not motivating, that's for sure.
Yeah.
Like if you're gonna use that as a motivational statement, then you're giving me, a 30-minute talk along with that statement. So
Well put. Yeah.
Yeah. All right.
I'll
Is
see you guys
anybody
all
else?
next week. Thank you again.
Yeah, I'll see you. I'll see you on Discord. So anybody else have any questions? There's still quite a number of people in here. So by quite a number, I mean 3, but. All right. Well, David and Jim and Kelsey, I hope to see you next week. Thanks for attending once again. Kelsey, feel free to pop by my office if you have any specific questions about anything that was said today. I have absolutely no problem clarifying.
Thanks,
So,
Anthony.
Yep, I'll see you, Jim. Thanks again.
And I meant great that you had math majors attending, not that they were lost.
No, I told my math majors you should be going to talks. It doesn't matter if you're lost.
Yeah, I think it's great that they're attending. Excellent.
Yeah.
Next week.
Yep, I'll see ya.